All right, we're continuing with Chapter 2 of the geometry textbook. In this video, we're going to go through the second section, which talks about indirect proofs. So this is a section that deals with proof techniques. And again, as I mentioned, we're not going to work any example problems related to things like mathematical proofs, but we are going to go ahead and read through sections like this. So let's take a look at the idea of an indirect proof. All right, you might have heard of a proof like this. Another way you can say indirect proof is proof by contradiction. Okay, so if you're going to try and prove something by contradiction, that means you're doing an indirect proof. So, okay, let P to Q represent a conditional statement. If P, then Q, all right? The following statements are related to this conditional statement, also called an implication. So yeah, you can think of a conditional statement like if P, then Q as an implication, because if P, then that implies Q. All right, now recall that this symbol here means it's like not, the negation of a statement, the opposite of a statement. So like I eat spaghetti is a statement, then not of that statement is I don't eat spaghetti. Okay, so let's think about these four scenarios here related to a conditional statement. So here's the conditional or the implication, if P, then Q. Okay, now there's the converse of that, if Q, then P, like is that was like related to reversibility. Okay, but then you have the inverse of the conditional statement, which you just take the conditional and you make each of these not. So not P, then not Q, or if not P, then not Q. But then there's also the inverse of the converse, and that's called the contrapositive of the conditional. So if not Q, then not P. So, okay, you've got the conditional statement, then there's the converse of the conditional statement, the inverse of the conditional statement, or the contrapositive of the conditional statement. So all of these, the terms converse, inverse, and contrapositive are all related to the conditional statement. Okay? So if you have a converse, then you flip Q, then P. If you have an inverse, then you're saying you don't flip P and Q, you just say not, if not P, then not Q. If you have a contrapositive, then you're flipping P and Q and doing the inverse. You're saying, if not Q, then not P. And now you can also look at it like this, the contrapositive is the inverse of the converse. And you can look at it like the inverse is the converse of the contrapositive. So, but this is just notation, okay? All right, so let's take a look at an example here. We're given this conditional statement. If Tim lives in San Diego, then he lives in California. That's the conditional statement. So what's the converse of that? Well, that's if Tim lives in California, then he lives in San Diego. Okay, and well, we can also think about, so this is a true statement, right? If Tim lives in San Diego, then he lives in California. That's true. Now, the converse, if Tim lives in California, then he lives in San Diego, that's not necessarily true. Like we'd call that false. I mean, it could be true, but in general, it's, we want to make statements that are either 100% true or 100% false. So we'd say that's false, the converse. What about the inverse? So that would be, if Tim does not live in San Diego, then he does not live in California. That's false as well. I mean, he could live in Los Angeles. He cannot live in San Diego but still live in California. That's false. Okay, now what about the contrapositive of this statement? Okay, if Tim does not live in California, then he does not live in San Diego. That's true, right? If he doesn't live in California, then he can't live in San Diego. Okay, so for that statement, we got true, false, false, true. So in general, the conditional statement and its contrapositive are either both true or both false. Similarly, the converse and the inverse are also either both true or both false. So that's interesting. So, you're given this starting conditional statement. There was four slots here. The actual original statement, the converse, the inverse, the contrapositive. In general, we can think about it like if this is true, then this is going to be true. If this is false, then this is going to be false. And same idea here with the ones in the middle. Either these are both true or these are both false. Now, just because this is true here, just because this is true doesn't mean that just because like these two are true doesn't mean that these two have to be false. Right? No, it depends. These could all be true. It just means that it's just the associated pairs are going to both be the same. Okay, for the conditional statement that follows, give the converse, inverse, and contrapositive. So, okay, let's do this again. If two angles are vertical angles, then they are congruent angles. So that's the conditional statement. All right, so we've got, that's true, right? If two angles are vertical angles, then they are going to be congruent. That's universally true. So now the converse of that would be two angles are congruent angles, then they are vertical angles. That's false. That's false. I mean, we could do, here's two angles that are, this perpendicular line here, these two adjacent angles, those are congruent angles. Are they vertical angles? No. Okay, now what about the inverse? So if two angles are not vertical angles, then they are not congruent angles. Well, that's false as well. Here's two angles that are not vertical angles, but they're congruent angles, so no, that's false. Okay, now what about the contrapositive of this? Okay, if two angles are not congruent angles, then they are not vertical angles. That's true. That's true, because if two angles aren't congruent, then they can't be vertical angles. They can't be. All right? So now they make this statement here that says if P, then Q, and if not Q, then not P are equivalent. In terms of what they're talking about is in general, the conditional statement and its contrapositive are going to be the equivalent, either both true or both false. Now, it's not stating this as like this is official 100% true in the same way that this statement, like they said, in general, you can think about that the conditional statement and its contrapositive are the same. And I believe why they're not putting a stamp on this as 100% is because there's different schools of thought in terms of proof techniques and logic that go back, centuries or whatever, and that some people might argue that this isn't universally true in the sense that a conditional statement and its contrapositive are always the same. But we're going to, in this textbook, we're gonna go use the school of thought that they are. And just to show you why that's a pretty solid postulate, it's like a double negative. A double negative is always in congruence with the original statement, either true or false. Like they give an example here. The Venn diagrams can be used to explain why the conditional statement if P then Q and its contrapositive are equivalent. The relationship if P then Q is represented. Yeah. So, okay, let's think about the statement that the conditional statement, if you live in London, then you live in England, right? If you live in London, then you live in England. Okay. So P is if you live in London. Q, it means that you live in England because you don't, every single location in all of London is within England. So this is entirely a subset of Q, but you can live other places in England and not live in London, right? So you can see how it's like if P, then if you have a conditional statement that's true, then the P is a subset of Q. Now, if we think about the contrapositive, if you don't live in England, which means it's anything outside of here, then you don't live in London. Well, of course, if you're not in Q, if you're not in Q, then you can't be in P. Okay, and so it's like a double negative, right? If I eat macaroni and cheese tonight, I will be happy. Okay, contrapositive. If I don't eat macaroni and cheese tonight, then I will not be happy, right? So like this statement here of that the contrapositive is always in congruence with the original statement seems like pretty good logic. That's a good postulate. And that's what indirect proofs are based off of, this assumption, you could say. Okay, the law of negative inference, or you could say the law of contraposition. Consider the following circumstances and accept each premise as true. So if Matt cleans his room, then he will go to the movie. So we're assuming that's universally true. Now, Matt does not go to the movie. Okay, so you have an if P then Q, then you have a not Q, and that's going to imply, in this case, not P, is what they're saying here. Because we can conclude that, well, if Matt doesn't go to the movie, then that means he didn't clean his room. So this backdoor reasoning is based on the fact that the truth of P implies the truth of it. This backdoor reasoning is based on our assumption of that the contrapositive is incongruous with the original statement. And this is universally true. So here they give the law of negative inference, or the law of contraposition. So if P then Q, that's true, and then you have a circumstance of not Q, then that is going to imply that not P is the conclusion. Now, this should look familiar. In the opening section in section 1.1, we looked at the law of detachment. The law of detachment was if P then Q, and then P takes place, then the conclusion is that Q. So if I eat macaroni and cheese, I will be happy. I ate macaroni and cheese, conclusion, I'm happy. Here it's if P then Q, but then not Q implies not P. Okay? So use the law of negative inference to draw a valid conclusion for this argument. So if the weather is nice Friday, we will go on a picnic. So if P, then Q. But now in this case, we have not Q takes place, so we didn't go on the picnic. That means the weather on Friday must not have been nice. Okay? So, like the law of detachment, the law of negative inference, or the law of contraposition, is a form of deduction. So deduction is when you had intuition, you had induction, you had deduction. Intuition was just like, your gut feeling about something. Induction was like you're doing experiments, and then deduction was actually writing the formal argument. And so you can think about like proofs are a form of deduction. Any form of proof is a form of deduction. You've done the experiments, you have the evidence to say, okay, I believe this is true, and I can prove it, and so now you're going to use deduction to prove it. All right, but whereas the law of detachment characterizes the method of direct proof, found in the preceding sections, the law of negative inference characterizes the method of proof known as indirect proof. So, okay, again, the law of detachment, the if P then Q, and then P happens, that implies Q, that's a method of direct proof, and that's what all the proofs we've looked at so far are this form of direct proof. But the law of negative inference, or the law of contraposition, is an indirect proof method. We haven't done any of these yet. So let's take a look at this indirect proof method. You need to know when to use the indirect method of proof. Often the theorem to be proved has the form if P then Q, in which Q is a negation and denies some claim. For instance, an indirect proof might be best if Q reads in one of these ways: C is not equal to D, or L is not perpendicular to M. So yeah, you might have some statements that you want to prove that have these negations in them. Is not this, is not that, and that's where you could consider an indirect proof. But however, we will see in example 5 coming up that the indirect method can be used to prove, you can use an indirect proof. It's not like this is a requirement. Okay. It will be used to prove that line L is parallel to line M. Indirect proof is also used for proving existence and uniqueness theorems, which we'll see in an upcoming example. The method of indirect proof is illustrated in example 3. All indirect proofs in this book are given in paragraph form, as are some of the direct proofs. So, okay, in any paragraph proof, each statement must still be justified. Because of the need to order your statements properly, writing any type of proof may have a positive impact on the essays. Yeah, okay, so they're gonna do the proof in paragraph form, not like line form. All right, so here we go. Let's take a look at this example. So, okay, in figure 2.12, ray BA is not perpendicular to ray BD. Okay, prove that angle 1 and angle 2 are not complementary. Okay, that angle 1 and angle 2 don't sum to 90. Okay, so the first thing that you do in an indirect proof is you're going to say, so you're going to suppose that and state the opposite of the proof statement. So suppose that angle 1 and angle 2 are complementary. Suppose that that's the case. Okay? Then from there, you're going to make factual statements with reasons that eventually you want to say something about what's given. You don't know what it's going to be, but we want to make a statement about what's given. So in other words, about the perpendicularity of we're supposing that angles 1 and angles 2 are complementary. So with that, let's try and make a statement about what that means about a relation between ray BA and BD. Okay, so if they are complementary, angles 1 and angles 2, then the measure of angle 1 plus the measure of angle 2 is 90 degrees. Yes, that's what complementary means. Okay. Now, we also know that since these are adjacent angles and they're contained within ray BA and BD, that measure of angle 1 plus measure of angle 2 sums to the measure of angle ABD, but the measure of angle ABD is 90 if they're complementary. Okay. So in that case, we know that angle ABD is a right angle because that's the definition of right angle. It's 90 degrees. Okay, but in turn, then, we know that means that ray BA and BD must be perpendicular because that's kind of a consequence of two lines being perpendicular, that the angle between them that they create is 90 degrees. Okay, but this contradicts the given hypothesis. Therefore, the supposition must be false, and it follows that angle 1 and angle 2 are not complementary. So what do they mean by this last statement here? This contradicts the given hypothesis. Well, what we're trying to do is we're taking advantage of the contrapositive in the original conditional statement being joined, like being, incongruence. So we've made a contradiction about the proof statement, right? So what we would like to do is go through some reasons and then come up with also contradict the given statement, because then we have this double negative. Like that's the idea of the proof by contradiction. The idea is we're saying if this is true, if what we're given this and we're trying to prove this. So if this is going to be true, this given in this proof statement, then it can't be the case that the not of this implies the truth of this. That cannot be the case. That would be a contradiction. So like, okay, if I eat macaroni and cheese tonight, then I will be happy. So now if I analyze the situation and I found that, okay, so if I say I didn't eat macaroni and cheese tonight, but I was happy, well, that's if I found that to be true, well, then that's a contradiction to the original statement. That can't be the case for the original statement to be true. I have to be able to find that if I didn't eat macaroni and cheese tonight, then I'm not happy. I have to. If I give the not the opposite of the conclusion statement, then I also need to find the opposite of the given statement to be true as well. If I didn't eat macaroni and cheese tonight, then I'm not happy, and that's what we showed here. We showed that if angles 1 and angles 2 are complementary, then BA and BD are perpendicular. Since that's true, then the contrapositive of that is also going to be true. So that's an example of an indirect proof or a proof by contradiction. So, okay, in all indirect proofs, the first statement takes the form, suppose or assume the exact opposite of the proof statement. Right, so that's going to be, for any indirect proof, the opening statement's going to be like, suppose that, and state the not of the proof statement. By its very nature, such a statement cannot be supported, even though every other statement in the proof can be justified. Thus, when a contradiction is reached, the finger of blame points to the supposition. Yeah, it can't be proved in relate. They're saying what they're talking about is that you make this statement here. That's the opposite of prove, but you still are kind of assuming that you have this as a given. That's what they're saying. You stated the opposite, but with that you're still thinking about what's given. You're trying to prove the opposite with what's in conjunction with what's given. But if the proof is going to be, the actual proof in general is going to be true, then that statement you made, that supposition can't be supported, though every other statement in the proof is actually correct. Thus, when a contradiction is reached, the finger of blame points to the supposition. Having reached a contradiction, we may say that the chain involving not Q has failed and is false. In effect, the double negative is equivalent to Q. Thus, our only recourse is to conclude that Q is true. Following is an outline of this technique. So yeah, here's a summary of the indirect proof method. So to prove the statement, if P then Q, or to complete the proof problem of the form. So given P, prove Q, we're going to say, okay, suppose not Q is true. Suppose that not Q is true, even in the context that we're given P. Suppose that not Q is true. Then you want to start giving reasons and eventually make a statement about P that can't be true. If you suppose that not Q is true and you show that, well, there's no way that P in that case could be true, then you've proven based on the contraposition and the original conditional statement need to be the same. You've proven the truth of the original statement from that perspective. Okay, the contradiction found in an indirect proof often takes the form Q and not Q, which cannot be true. Thus, the assumed statement not Q has forced the conclusion not P. Asserting that not Q implies not P is true. Then the desired theorem, if P then Q, which is equivalent to the contrapositive of not P then not Q, is also true. Exactly. Okay, the first line of an indirect proof is going to be suppose the opposite of the proof statement is true. Right. So let's look at another example. Complete a formal proof of the following theorem. So, okay, if two lines are cut by a transversal so that corresponding angles are not congruent, then the two lines are not parallel. Okay, so we're given that two lines are cut by a transversal so that corresponding angles are not congruent. So here's these two lines cut by a transversal, and they say angle 1 is not congruent to angle 5. Then that means that the two lines are not parallel. We want to prove this. So we're going to start by assuming that, what if L was parallel to M? Okay, what if L was parallel to M? Then, okay, in that case, we know that corresponding angles are going to be congruent. We've already shown that. But angle 1 is not congruent to angle 5, but that contradicts the given statement. So therefore, L can't be parallel to M. And, you know, this is interesting because you can think about it. It's kind of like if we had two lines and we didn't know if they were parallel or not. Well, but let's assume that they were parallel. Well, then we know there's all kinds of information about these 8 angles that come from the two lines being parallel, right? Corresponding angles are congruent. You've got the opposite interior angles, alternate interior angles, alternate exterior angles are congruent. So what's the minimum amount of information you need to show that about these angles to show that to prove that two lines are parallel, right? It's interesting to think about. Not like here, we didn't prove that the two lines were parallel in this statement. We proved that they weren't parallel. Okay, just note that. We proved that the two lines, we found that there were two corresponding angles that weren't congruent, then they can't be parallel. They can't be. That's what we proved here indirectly. Now, what about, could we say that if you have two lines, you don't know if they're parallel or not, but if you find that the corresponding angles are congruent, does that guarantee that they're parallel? Well, is it possible that you could have corresponding angles be congruent, but opposite interior angles aren't congruent? I don't know. You have to think about it, right? But again, all we proved here was that there's no way if you find you have a transversal cutting across two lines and you find that corresponding angles aren't congruent, then those lines cannot be parallel. We just proved that indirectly. All right, the versatility of the indirect proof is shown in the final examples of this section. The indirect proofs preceding example 5 contain a negation in the conclusion. The proofs in the final illustrations use the indirect method to arrive at a positive conclusion. So yeah, this was, we were told that one criteria you can think about to when to use an indirect proof was if you have some statements like, if this is not true, then that's not true. But you can still use an indirect proof even if it's not involving these negative statements in the given, in the proof. So, okay, in figure 2.14, plane T intersects parallel planes P and Q in lines L and M respectively. Okay, plane T intersects parallel planes P and Q and the resulting intersection of the lines L and M. Prove that L is parallel to M. All right, so there's no negatives here, but let's still try and use an indirect proof. So, okay, let's assume that L is not parallel to M. Okay, assume that L is not parallel to M. All right, so let me just try and talk through this more informally. Okay, L is not parallel to M. Well, the first thing is that if planes P and Q are parallel, then does that mean that if you pick any two lines from P and pick any line from P and any line from Q, that those two lines must be parallel? Well, no, not necessarily, because you could have the case they could be skew. Like you could have this line and this line are skew. But 100% they're not going to intersect. That's the meaning of two parallel planes. Okay, but we know, though, that these two lines are going to be contained in the same plane because that's part of the given. So if you have two lines that don't intersect and they're also contained in the same plane, they're parallel. So there's no way that L could not be parallel to M in this scenario. You see? So we've proved it by contradiction. So let's read how they write it. Assume that L is not parallel to M, then L and M intersect at some point A. They do? That's not true. They could be skew. But if so, point A must be on both planes P and Q, which means that the planes P and Q intersect, but P and Q are parallel by the hypothesis. Therefore, the assumption that L and M are not parallel must be false, and it follows that L is parallel to M. What? I can draw a line in plane P and a line in plane Q. They don't intersect, but they are not parallel. Maybe they're going with the assumption that lines L and M are in the same plane, plane T. In that case, if you're assuming that, yeah, that's what they must be doing. If you're assuming that they're in the same plane because plane T cuts across and L and M are not parallel, then they must intersect. If you have two lines in the same plane that aren't parallel, then that means they intersect. But if line L is in plane P and line M is in plane Q and they intersect, then the two planes can't be parallel. So there's a contradiction. So yeah, you can see how you can still use indirect proofs even if you don't have these negative statements in the given and the proved. All right, prove the statement, the bisector of an angle is unique. Okay, so yeah, there's only one, there's one and only one bisector of an angle. You can't, they're saying like, let's say this is a bisector, you can't draw another line that's different from this, or another ray that's different from this ray that also bisects angle BAC. So given that ray BD bisects angle BAC, prove that ray BD is the only bisector for angle ABC. So, okay, well, let's suppose that we have another ray BE, that also bisects angle BAC. Okay, so, obviously this can't be true, but let's see how they rationalize this. By the angle addition postulate, the measure of angle ABD is equal to the measure of angle ABE plus the measure of angle EBD, okay? By substitution, 1/2 of the measure of angle ABC is equal to 1/2 the measure of angle ABC plus the measure of angle EBD. And they're substituting this here for the measure of angle ABD. But then the measure of angle EBD would be 0. It has to be 0 in order for this equality to hold here. And an angle having EBD be 0 doesn't make any sense, because then we wouldn't have two unique rays. And technically this contradiction comes from the protractor postulate, which stated that the measure of an angle is a unique positive number. So, like, in other words, there's clearly some angle here that's not 0. That's what they're saying. There has to be. So, therefore, there's a contradiction, and so that proves the original conditional statement. Okay, so that's the idea of an indirect proof, or a proof by contradiction. We're not going to work any example problems from this section, so let's move on to section 2.3.